Okay. Can everyone see my screen? Yep. Okay. So thanks for the introduction of Zhenchang. So as Zhenchang just introduced, I'm a PhD student under Dr. Zhenchang's supervision, and this is my final year, and this is my final PhD competition seminar. So during this presentation, I will introduce what I did in the past few years, and I hope you guys will enjoy it and maybe probably find it fun and maybe get some interesting ideas from my presentation. It will be pleasure of mine. Okay, so yeah, so the topic of my presentation today is video intelligence for GUI automation and beyond. And please allow me to first give some background of this project, of this presentation. So graphic user interface, also called GUI or GUI, is critical in modern software engineering. So graphic user interface is the major means for human to interact with the application and to use the to get access to the functionalities of apps or access to the underlying system. And with the advancement of information technology, as well as the widespread of mobile devices in nowadays, so the graphic user interface is now dominate the way we interact with our devices. So it makes the GUI development grow into an independent and large topic to research and to study in the field of software engineering. So for the GUI development, generally it contains 4 stages. So first we have the GUI requirement, and then in which we just elicitate what our client really want, and then we have the GUI design, in which we just draw some wireframe and we just create some GUI prototype to show the visual effect of the final app and GUIs. And then we have the GUI programming, in which we just implement the GUI design into working code, and that can be run on the browser or the mobile phone or the personal computer. So, and the final stage of the GUI development is GUI testing, in which we test and verify and validate the program we just developed, and to say if the GUI is rendered and can be run properly on various devices. So during those four different stages, we have lots of specific challenges, and which makes the research field of software engineering to pay more attention to automate the process in GUI development. And you can, as you can see here, the GUI automation tasks, which involve like multiple stages of GUI development, have developed lots of interesting research projects and topics. So for example, we here have the wireframe generation and validation from the GUI requirement automatically, and we have the code generation from image, and we also have the automated testing for GUI and mobile app. So here are some visualized example of the GUI automation tasks. So for example, in the GUI design stage, we have the UI search, in which we just input some interesting GUI, and the search engine will just search around its database to and return us some similar or related GUIs to us, for us to gain more inspirations. And for the development stage, for the programming stage, we have the UI image to code generation, in which we just need to input the GUI prototype. We just draw using some software like Photoshop or something, or and it will automatically generate the skeleton or even the working front-end code to us. So which just eliminate some laborious and repetitive work of the developer and the designer. And then, so during the daily use of the app, we also have some automation tasks here. So for example, we have the intention auto execution tasks here. So in this task, the user just need to tell the form what the intent of the user. So for example, the user just need to say, change the display language, and the application will automatically execute some operations to fulfill the purpose. So lots of those fancy and advanced automation tasks in common need the GUI intelligence. So GUI intelligence is to understand what is happening on the GUI and what is the compositions on the GUI. So GUI intelligence is a foundation for all of those automation tasks. Especially the value GUI intelligence recently draw more and more attention from the research field of software engineering because of many advantages. So for example, the value GUI intelligence, it tries to understand the GUI from the value aspect or from the image aspect. So it only requires the image, and it just emulates how a human being viewing the GUI. So we just view the GUI through our eyes, right? And we do not have any access to the underlying system and the underlying like running code or something. So the value GUI intelligence does not demand any underlying metadata and does not demand any intrusive hacking into the app or the device. So it has lots of advantages, and it is necessary for some applications and during under various environments. So for example, for some system, we do not have the availability or the access to the underlying system, which means we cannot get the underlying code or metadata of that app. So to analyze those apps on those closed system, we have to rely on the GUI visual intelligence. So the GUI visual intelligence is the major project I am researching on. And just like other artificial intelligence or AI, so the purpose is to perceiving and inferring information to take action that maximum its chance to achieving goals, right? So this is a general purpose of AI. Similar to GUI visual intelligence, here we also want to perceive or to say the information and infer or understand the information to guide the actions that can be done for many fancy and advanced GUI automation tasks. So here we have the step here. The first, we have the GUI image, and the very first step is to say what is on the image, which is detection, the GUI elements from the image. And next, we have to understand how those elements organize and what's the rules of those elements to guide the downstream tasks. And after we have such like basic value understanding, we then can make some actions. So for example, here I take two examples here. The first acting example is the automated testing, and the second is the image to code generation tasks, which I will introduce in later later stage of my presentation. So after introduction of those background, let me just first introduce the very first step of GUI visual intelligence, which is saying what is on the GUI. So seeing what is on the GUI is equal to detecting the individual elements from the image. So this task, just speaking of this task, it just remind people a popular topic in the computer science or the computer vision, which is object detection tasks. So the general object detection is to extract or identify the meaningful objects from some nature photos. So for example, here we got a photo here, and the purpose of the object detection is to detect the dog and the bicycle and the car from the photo, right? So it is quite similar to the objective of the GUI element detection. However, the GUI is visually special from the nature photos because of lots of reasons. So first of all, the GUI, it is a more packed thing, which means it has like much more elements on it compared to the nature photo. So for example, take this GUI as example. So this tiny GUI itself just has like 46 various elements on it. And all of those various elements are very close by to each other, which makes the detection quite challenging compared to other like normal tasks of nature object detection. And second, the content on the GUI is literally the content of the GUI. Literally can be anything, right? It can be some map, it can be some like photo, it can be some animation, some virtual objects, right? So the compositions of the GUI is very diverse. It's not just like some nature object detection in some nature photo, because we just have limited number of classes of objects, right? But in the GUI detection, it got significantly more objects here in different classes. And the next GUI value characteristics is that it is a mix of texture and graphical contents, which means it's not just to have like some value objects here. It also contains many text elements on the GUI. And but one good thing for GUI is that it's although like despite all of those challenges, in the GUI, it usually has a clear background. So for example, take those three GUIs, for example. Although we have like various elements, so no matter the texture or graphical, the background is just clear, right? And in terms of the specific GUI elements, so you can say we have the large in-class variance for GUI elements, which means even those elements are in the same class, they can be really different, right? As you can say, some elements here, like for example, the image view. So although all of those three images are image view, but they are just totally different, right? And besides, we also have the high interclass similarity. So for some GUI elements that's in different classes, they are actually very similar. So for example, the edit text here and the text view here, they are just fundamentally, they are just text, right? So all of those things just complicate the task to detect and classify the GUI elements from GUI image. So so talking about the object detection, there are, generally speaking, there are two methods here. So the one is a old-fashioned based on image processing, and so in this method, we just use some white box algorithms to try to do some pixel level analysis and to so that we can have some like edge detection or gradient analyze, something like that. But they're all just pixel level black box algorithms, which are handmade. And then we have the deep learning here, which is recently really popular or dominate in computer vision. So for the deep learning deep learning approach, we just have a black box model here, and we try to through like massive data set to it and try to let it teach itself to learn the value clues on those images and try to like achieve the goals they have to. So for both of those methods, we have some previous works in GUI detection that tries to use both old-fashioned or the deep learning-based approach to detect the elements from the GUI images. But for the old-fashioned or the image processing-based approach, the problem with it is that it detects. So traditionally, especially for some like popular methods, for example, the canny edge detection or sober edge detection, the problem with it is that they all detect too much fine-grained features. So, for example, you can take a look at the first image here. It's just produced too many texture informations here, and it's not helpful for the detection of the GUI elements here at all, right? And it's unable to extract the text on the image because it just mix the text and the background image here, right? And also because it is based on some pixel level analysis, so it's very sensitive to noise. So here at the right-hand side here, you can see the results of two previous approach that based on traditional image processing approach, which is just whose performance is are just really poor, right? And on the other hand, for the deep learning based approach, many previous works just try to directly use the popular models, for example, such as the ULU or FastSN or even some node anchor based model, the Internet. But the problem with the deep learning model is that it's first of all, it requires massive specific data set to train. But such large data set is especially late in the GUI in the GUI research field, and also it just produced some inaccurate bounding box due to the regression rationale of it, right? And it would mix the text and the non-text elements together to just hurt the final result of the detection. So here you can see this is an experimental result of us, which shows all of those existing approach based on old-fashioned or the deep learning models are just performing really poor. So in conclusion, we now really need a GUI specific element detector that takes the consideration of some special GUI value properties. To this end, we introduce our own GUI-specific element detector, the UIED. So here we can say the UIED. So try to extract the non-text elements by some specifically designed for design algorithms. So, for example, the first image is a GUI, and the second is the edge detection results by some exciting and popular old-fashioned image processing algorithms, which is canny or sober, which is really messy here, right? But the third image just show the GUI spannerizations, which is quite clear to combine to extract the widget without over segmenting it or under segmenting it, right? So the over segmenting is just means we segment we segment one GUI element into several pieces by mistake. So overall, UIED just adopts a divide and conquer strategy, which means it first detects the non-text element through some like specifically designed algorithms based on old-fashioned pixel level analysis. And it also detects the text using some advanced text recognizer, just as such as the Google OCR or EAST. And then and finally it just merged the results from those two stages. So here are some results of UIED detection, and you can say so the green bounding box the green bounding box means the element is non-text, and the red one means they are text. And here you can say UIED performs really well in like various GUIs. Even for like the third one, even for the third GUI where there is a complicated map on it, but the UID can still perform quite well. So we also developed and published a interactive website or so web-based tool for UID. The link is just shown here. This is a link of our website, and in which you can try this tool, and you can try different models to see the performance. And also we provide an interactive dashboard for adjusting the detection results and to reuse the detected component. So after the basic seeing or the basic detection of individual and separate elements, the next stage is to understand what understand high level knowledge in the GUI, right? So as you can see here, the first one is the original GUI image, and the second one is the detection result. And then after we have those detection results, the next stage is that we want to understand the layout information of the GUI, right? Because the GUI is not just simply a combination or a stack of separate elements. It organizes the elements in some element and layout blocks. So for example, as a human, we can say that in this GUI, there should be a big list of the user, including the user portfolio photo and the user name, user introduction. And we, as a human, we can also notice that there is a multi-tab menu on the top of the UI, right? So to this end, so as a human being, we can intuitively perceive the layout information of the GUI, but to empower such ability to the computer is very challenging, because it's now the algorithm approach the computer. It's now can only acquire the basic information of separate GUI elements, right? So how to do it? Let's just step back and think about how we human being actually vary the objects, or how we human being like perceive the groups instead of separate components. So to this end, we resort to a well-established psychological theory, the Gestalt theory. So the Gestalt theory just states that we see patterns and wholes rather than components and parts. So how to understand it? I will give you some interesting example to explain it. So for example, here we have a set of blue circles here, right? And we cannot see any patterns yet. But what if I just draw a bounding box to enclose some of the circles? We would intuitively group or relate or make those make those circles enclosed in the same bounding box related, right? We would perceive those circles that are included in the box as a related group rather than those are not, right? And also, if I draw a line here to connect multiple circles, so if I connect those circles, we would intuitively perceive those connected circles as more related than those are not, right? So this is called connectedness principle, and which just states we perceive elements connected by uniform value properties, so such as a box or a line, as more related than those are not connected. And the second principle is similarity principle. In this principle, so what if I just change some colors of so the colors of some of the circles? So for example, I just change the color of those 3 circles from blue to yellow. So we would intuitively just relate, like group those 3 circles in same colors together, right? So and also, what if I just change the shape of some of them? So for example, if I just change the shape of the 3 circles, and we would also intuitively group those in the same shape together as a related group, right? So this is called similarity principle. So it states that the elements are perceptually grounded together if they are visually similar to each other. The next one is and the third one is proximity principle. So if I just move a row of the circles up a little bit, we would notice that there are 2 groups of circles here. So the one is the row at the top, and the other group is the 3 rows at the bottom. So if I just move another row a little bit together to get approximate with the top one, we would intuitively group those 4 rows of circles into 2 groups. So this is called proximity principle. So it says when people say an assortment of objects, they tend to group the objects that are close to each other or approximate to each other. And the last one is the continuity principle. So this is a little bit abstract, but it can still be understood. So when we saw the elements, we would saw the elements that are arranged in a line or curve are more related. So for example, here we can see actually 2 curves of circles here, right? Because of the continuity principle. So with those 4 strong principles of how we human beings perceive objects, we can understand how our perception progress work. So with this understanding, we can now develop our algorithms to help us to group the individual, the separate, the concrete GUI elements into different groups and different layout blocks, right? So just in line with those 4 principles, the first principle is the connectedness. So in GUI element grouping, we use the connectedness principle by recognizing the box container in the GUI. So for example, here in this GUI image, we can see that there are some containers here, right? Those containers just contain many like multiple elements within it, and so we would perceive that those elements contained in the same container as a group. So this is the underlying rationale to apply the connectedness principle in GUI element grouping. And for the second principle, the similarity principle. So for the similarity principle says that we would tend to group some objects with the same value properties together, right? So same for the GUI elements. If those elements have or share some common value properties, just such as the size, the color, the shape, or even the element, the position element, they would be grouped together. So still this GUI. And if we look at the bottom, eight elements here, so we got four non-text wedges here, and we got four text elements here. So we can say that those four wedges, those four non-text wedges, just have the similar size and elements, right? So we tend to group them together as a group, and you can say here we just assign them to the same group, the NT2 group. And same for the text, we just assign the four text elements at the bottom into the same group, the T1 group. And here we can say a more clear example here. So for those images here at the left hand side, so all of those images here just have the same shape, they are all circle, and have the same size, also have the same vertical element. So we tend to group them together as a cluster, right? So here we have, here we just group those elements together as the NT0. So same for other groups, same for other elements. And to this end, in detail, to this end, we first cluster the wedges or the elements with similar shape or placements together through a unsupervised clustering algorithms, the DB scan. But understandably, lots of elements would be clustered multiple times because they would share the similar variability with multiple different elements, right? So to resolve this clustering conflict, we use the similarity principle again, and to compare the similarity of the variability between these conflicting elements and all of those groups, and then finally assign this conflicting element to the group with the largest similarity. So next we use the proximity principle to further group those clusters together. So for example, here we have two cluster or two groups here, right? The NT2 and the T1. And we will notice that those two groups are really close to each other, and they have the same members within those groups in terms of the number and the element of those members. So we further group those two proximate groups together as a large group. And you can say this is a final result of the grouping. And for the sake of presentation, we denote the pairs of matched atoms in each group as a subgroup, as you can say. So those are the subgroups for the sake of presentation. We just paint those subgroups as the same color. And so finally, to use the continuity principle, we actually use this principle to correct some errors of the detection. So for example, here we have two parts of different GUIs, and for the first one, we can notice that for the first one we have like so we are supposed to have 8 non-text elements and 8 text elements in this GUI, right? However, because of the mistake of the detection, it's like wrongly discards this tiny icon here, because it's just too tiny, and the UID just regards it as a noise and just fill it out. So for this object, so for those objects, we use our grouping algorithms, and we tried, this is so we use our grouping algorithms, and we will get a group of those 16 elements, and we would have 8 different subgroups here, right? And so looking at from examining at those 8 subgroups, we would easily to notice that 7 of those subgroups have 2 elements within them. However, just only one subgroup just have 1 element in it, right? So which means this subgroup could have some mistake. And then we just use this principle to try to use our detector to detect it again with using restriction and parameters to try to fix this error. Also, for the second one, for the misclassification, so we can say the green box is non-text and the red box is text. So we can say actually the two subgroups have a non-text element on the right top side, right? However, the second one just have a text element on the same relevant position. So according to the continuity principle, as well as the majority winning principle, we would correct this one from text element to non-text element. So this is the result of our wedge grouping approach, and you can say this approach is capable of handling many different cases. So, for example, for this group, for this GUI, we first detect it. We first detect the wedges or the elements, and then we group it. Which means we recognize there are at least two lists of elements in this GUI, right? So also for this one, this complicated map GUI, we can still group those elements correctly. And also for some packed GUIs that contain many different wedges within it, we can still the approach is still able to handle it well. So it can not only, so this is the design prototype of GUI, it's not real GUI. Even for those design prototype, this approach can still handle it well. So this is the detailed performance of the quantitative performance of the grouping approach, which can be found in our original paper of this work. So next, after we have this basic detection and understanding of those GUI or the GUI information, we can then do some GUI automation acting. So with those understandings, it would be really helpful for us to perform some downstream automation tasks, which is acting. So we take the GUI auto testing, for example. What is GUI auto testing? In our case, in this scenario, the GUI auto testing is a common need in the GUI development. So for example, because of the widespread of large diversity of modern electronic devices, so the GUI would be displayed or rendered very differently in different devices, right? Because of the hardware environment, like the screen size, the resolution, and the software environment, which is the operating system. So you can say, even for the same app, the same GUI would be rendered differently in different devices. So to test the app, the developer have to run the app on various devices to verify the app could work properly. So traditionally, how do we do it? We just do some actions in one devices. So for example, we just click some elements on the first devices, and then we try to repeat this action on other devices, just clicking the same elements on other devices. And so for some tiny devices in which maybe the target element is out of the scope of the devices, we have to scroll the screen and to try to find it. So the problem with this manual testing is that it's really time consuming and laborious because of the plenty of repetitive operations it involves, right? So to solve this problem, one common one common means is the metadata-based record and replay. What is metadata-based record and replay? So we just do the actions. We just do the operation on one device, and the device will record our operations as an event, as an app event in the system, and then it will generate a event trace file. And we just take the event trace file to some replay agent and to inject those events and to try to replay it on other devices. So apparently this kind of practice, it just requires hacking into the apps through some certain APIs. And it's really hard to transfer the testing across different platforms, right? Because like the underlying system, the underlying code running environment is just totally different. And it requires heavy engineering efforts, and it requires the technical background to do such record and replay. So on the other hand, the vision-based record and replay is more generic. It is more general because it just requires the vision information or the image information. But there are lots of challenges in this vision-based record and replay. So, for example, the responsive layout changes because of the different size of the devices and the different positions of the GUI elements or widgets, and also, as I said before, on some small devices, the widget would just disappear because it was placed out of the scope of this current page, right? So all of those challenges just complicate the vision-based record and replay. So to this end, we propose the NICRO. We propose our own approach, the NICRO, which is the purely vision-based, non-intrusive, cross-devices and cross-platform GUI testing tool. So NICRO is composed of 3 components in the system. It has a virtual device farm, and it has a host computer, and it also has a robot system. So the host computer just runs the core algorithms, and those other 2 components just provide various devices. So both in either in virtual or in physical form. So this is a virtual device farm, and this is a robotic system, and you can see it's quite clear to say it can support lots of different devices, right? And for the core algorithm here, we first record the action and also collect all of the GUI images from various devices. And the first thing we will do is just detect the widget or the element. And then we would try to do some high-level understanding of it, for example, like the perceptual grouping. And then we try to match the widget on different GUIs from different devices. And we also do the GUI matching. And finally, after we found the corresponding elements, we just send the action to the virtual form or the robot system to execute the operations. So we use a multimodal information representation to represent the elements. We have its clips here, the image clips here, and we also have the texture content, and we also have its position, and besides, we also have its neighboring elements. And so like what element is next to it, and we also have its parent element if there is any. So NICROs, just as normal actions, NICROs support 2 kinds of different actions. The first one is widget-dependent actions, which is related to some widgets, which is like the click, long press, or text input. It also supports the widget-independent actions, for example, just like the sweeping or the scroll or the scrolling. So the workflow is that we just need to do some action in one source elements here. So for example, we just click this element here, and then in different devices, here we got 3 different devices. So for example, in the first one, virtual devices, it will first get the GUI image, and it will detect all those elements on this GUI, and then it will try to match this the corresponding target elements, and it will then perform the same or replace the same the same operations as we did in the source devices. And for some smaller ones, so for example, for the device 2 and device 3, if it haven't, like if it, so for example, because this one is smaller than this, and the target element is just out of the scope, out of the current page of this screen, right? So if we cannot match any elements on current page, what we will do is just we try to scroll it. So automatically scroll the current page and try to match it again. So for example, here we just scroll it, and we got a new GUI here, and we do the detection again and do the match again, and then we finally found it. So it's same for the physical ones. In the robotic system, we just first try to find it, but we haven't found it. Then we try to use the robot arm to scroll the screen and to get the screenshot and do the detection again and match it again. Then we finally found the target one. So to evaluate. So to evaluate the effectiveness of our approach, we use 28 apps in 14 different classes, and we use 8 different devices to test the performance of it. Which you can say the accuracy of our matching algorithm is just significantly outperform other baseline approach. And also the test case replay accuracy of our system is also we're like significantly outperforming other baselines. So all of those things I just introduced is visual intelligence that be applied on the GUI tasks, right? So, but however, this kind of visual intelligence for GUI is actually more general than just for GUI. It can be used in many beyond the tasks. Here we have here we take a very normal routine, the form filling, for example. So for form filling, so the usual practice for form filling just includes three different means here, right? So for example, we can handwriting to fill out the form. We can use some PDF editing tool to fill out the form, and we can also fill out some online form, right, on the website. So for the handwriting form filling, there are lots of problems with it. So it's hard to revise because it's physical filling, right? And it has low readability, especially if you have terrible handwriting, and you got some troubles with the submission. So you have to scan it. So you have to print it out and fill it and scan it back, which is really troublesome. And it's easy to fill out of the space if your writing is just quite large. So for the PDF filling, there are also lots of problems. For example, you have to adjust the element by yourself, which is really noisy sometimes, and it doesn't have any data check. It doesn't know. So for example, if it asks you to fill in some number, but if you just fill in some characters, so it's supposed to remind you that you are filling the wrong data type, right? But this functionality is not supported in the PDF filling, and there is no filling assistance at all in PDF fillings. So for the online form input on some website, it is more interactive and accessible. It is easy to revise, and it is so it has lots of accessibility support, like the text to speech and the flexible text font adjustment. and you have lots of interactive features and collaborative features, right? So, however, to create such online form, sometimes it's not an easy task, especially for the people without any technical background. So the common means to build a online form is using some form builder. So for example, like the Google form. But the Google form and other like it are quite limited in terms of the style and the content and the customization. And if you really want to customize the online form you just made by those form builders, you have to have have a technical background to change the underlying render code of the online form. And the data, so many data, although we use the online form to do some to do the form filling, but in many cases, in many formal cases, we still need to store our data in a formal format for archive, like for filling some government forms, right? So something like that. So to this end, we just propose our own vision-based online form generator, the easy form. So the easy form just it can take 3 different formats of input. It can just take the photo of your paper form, or you can upload the original PDF file, or you can take the screenshot of the PDF file and input it to the easy form. And easy form will just convert the form into some online form with rich accessibility and interactivity support. So the approach architecture is shown here. So we first have the image, and we do 2 things. The first thing is to object detection recognition to recognize the text on the form, and then we recognize the basic shapes, for example, the rectangles and the lines, which could be the input field. And then we try to combine the shape elements and the text into the input components, and then we just transfer or just convert those detected input components into some interactive website, interactive online form, and where the user can easily input their data. So as I said, so the first thing to do is to detect the basic shape elements on the form. So what we do is exactly, or not exactly, is similar to what we do for the non-text GUI element detection. So here we can say we first do the binary map, and we do the detection. So we do the counter detection for those elements, and then we can recognize all of those rectangular, line, and square elements on this on the form. And then next we do the OCR detection to extract the text from it. So after we have the text and the shape elements, we can combine those 2 together to according to some heuristics to form the input component. So for example, we have here 5-6 types of input components. So for example, the first one is just have a text on the left and a rectangle on the right. So, and we also have some checkbox, and we also have a text box here. So we try to combine the elements and the text, and so according to this heuristics. So this is a heuristics of our approach, and this is the visualized result of the combination. So for example, here we can say we have the text here, and we realize that there is a rectangle just right beside this text, and they are really close to each other, and they have the horizontal element. So we identify, so this text should be the input label, and this and the rectangle beside it should be the input field of, and so we just combine those 2 together into a entire input component here, right? So same for those different things. So for example, here we have a line of text on the top, and we just found out that are two rectangles underneath it. And we, according to the heuristics here, we will realize that it could be a second type. The I2, the I2 of input component. So we combine them together and to form a component, a input component. So next, we also dissect the form into sequential sections according to the title. So for example, here we have the part A, part B, part C, right? So to better facilitate the form filling process, we try to dissect those this form into different sections, and so through the titles or subtitles here. So 1, 2, 3, 4, and here we have 4 sections here, and so for some special cases, so for example, this like multi-columns form, we also try to recognize the column and dissect the form into multi-columns and try to reorganize it into different sequence to convert it to a more clear and concise online form. So after doing that, we now have we now can generate our so after recognizing the input component and the layout structure, we can now generate our online form, and this is the result. So this is the input form, and this is the detection result, or the form component detection result, and this is the final result of the generated online form. And so our approach is capable of handling various forms. It can basically handling like more than 90% of the existing popular like common forms. So even for these forms, we can still recognize the input components here and generate the corresponding online form. And even for this one, which is a little bit more complicated, but we can still, but this approach can still handle it really well. And still, I also developed a interactive tool for you guys for the user to try our tool. And this is a link of our tool. And in this website, in this web-based tool, you can enjoy lots of accessibility features such as the flexible text size and the text to speech and the highlighting where you are currently typing, and the concise presentation. It also have some interactivity facilitation. So for example, the data validation, it will check if you are inputting the right format of data, and it would help you to preform some common or some your information such as your name and your age or something like that. And it would also give you lots of like foldable section. So because we now just dissect this form into different sections, and now we can fold it and to let the user just focus on their current section, or their current filling section. So this is the usage of our website. So you just need to go to the homepage and upload or just try some samples here, and you can use it to fill the form. And after the filling in, so we also support the signature function here. And after filling in the data, you can export the PDF, file, the filled PDF file plus the JSON file. So we to evaluate our tool, we perform a user study that's spanning a wide range of participants, including the different age groups and different occupation groups. So and we also ask some like lots of questions regarding the usability of our tool, and you can say so the user form here just outperform all other form filling ways. And also for this one is grouped by the different ages. So yeah, thanks for listening, and that's all for me to present all of my visual intelligence for GUI and beyond. And I hope you guys enjoying this presentation, and it would be my pleasure if you have some like interesting ideas inspired by my presentation. Okay. Thank you, guys.
Thank you very much, Mulong, for the presentation. As you can see, he did the great work and a lot of work in the past few years. So it took him a bit longer than 1 hour to present his research work. So I guess if you are interested to be asking some questions, feel free to stay here. If you have other tasks or errand, feel free to leave. And now I open the ground for some questions, and maybe we can have some questions and discussion for 5 to 10 minutes.
Yeah. Any question or ideas you want to chat with me? Or you can send me email after this presentation, and this is my personal website. You can go and check for more interesting project I did during my PhD or other times. Yeah.
If you feel like asking a question afterward, offline, we are all very accessible.
Yeah, just feel free, and we are more than glad to discuss with different people. Yeah. So those are this is my website, and you can go and check some other interesting projects I did before. Yep.
Okay. So if no questions, maybe conscious of time, maybe let's call it a day. And I thank you everyone again for attending the seminar. And hopefully you get some interesting connections to your work. And you're very welcome to contact us. And hope everyone have a great lunch. Okay.
Yeah, thanks for the participation, guys. Thank you.
Okay, thanks, Mulong. Thanks, everyone. Bye now.
See ya.